So welcome to the final video, the end of AP Chemistry 3 of 3, Spring of 2020 with Dr. Petty. All we have to do is go over the exam we've just completed and so on to the questions. So question 1, true and false. Lewis acids are always Bronsted acids? Certainly not. There are lots of things that are capable of latching onto a lone pair that are not protons, so that's false. A reaction with a large negative delta G will have a high rate of reaction. Nope. Kinetics and thermodynamics are separate. You can have a really favorable reaction with the bad kinetics and then it won't happen. Raising the temperature will change the value of an equilibrium constant. Yes, the rate constants depend on temperature, so changing the temperature will depend on the rate constants. That will shift the equilibrium. First order reactions always have consistent half-lives. Yes, that's characteristic of first order kinetics. And nickel metal will reduce magnesium plus 2 ions in solution. Well, that's a simple question of which one's a better reducing agent, nickel or magnesium. Go to our chart and look up the potentials. The nickel reduction potential minus 2.5, manganese minus 1.18, which means the manganese is going to has a worse reducing potential, meaning has a better oxidizing potential. So yes, the nickel will not reduce the manganese. The manganese would reduce nickel. An electrolysis cell plates out 6.13 grams of gold in 15 minutes from an aqueous potassium gold 3 chloride solution. What is the current flowing in the cell? Well, first step is, of course, balance the equation. It takes 3 electrons to reduce the gold plus 3 to gold 0. 6.13 grams divided by 96.97 gets us moles of gold. 1 mole of gold requires 3 Faradays. 1 Faraday is 96.485 coulombs, so we're going to need 9,008.27 coulombs. 15 minutes is 900 seconds, so 9,000 coulombs divided by 900 seconds, we have a current of 10 amperes. Given the following system, closed container at 100 degrees Celsius, indicate which of the following changes would push this to the left, right, or leave it unchanged. Decreasing the volume would raise the pressure. The only thing the system can do to reduce the pressure is to reduce the number of particles. So that would push it to the right. Add helium. None of the equilibrium cares about helium, won't have any effect. Lowering the temperature is removing heat. The system thinks heat's one of the products, so removing heat will cause the reaction to run to the right. And finally, of course, adding a catalyst at equilibrium is going to have no effect on the equilibrium. On to problem 4. Balance the following redox reaction taking place in acidic aqueous solution. The permanganate going to manganese plus 2. The manganese is plus 7 going to plus 2, so that's a change of minus 5. The 2 carbons are going from plus 2 to 0, so that's a change of 4. First number that includes 4 and 5 is 20. So we need 5 of the C2H6O, and we need 4 of the permanganates. To balance the charges, we're going to have 12 protons to the left side of the equation. And once we go through and account for everything else, we find out we have 11 water molecules on the right. That brings us to problem 5. Given the following information, answer these questions. What is the delta H0 for this reaction? Well, the delta H0 is the delta H of the products minus the delta H of the reactions. The heat of formation for the ethane minus 84.5 kilojoules. The heat of formation for the hydrogen as an element is 0. For the acetylene, plus 226.7 kilojoules per mole, so the delta H0 for the reaction minus 311.4 kilojoules. What is the delta S for this reaction? Well, that's the delta S of the products minus the delta S of the reactants. And in this case, of course, the hydrogen has lots of entropy, and there's 2 of them. And so what we find out is the delta S for this reaction minus 232.5 joules per Kelvin. What is the value of the equilibrium constant for this reaction under standard conditions? Well, we're first going to have to calculate the delta G0. So that's minus delta H0 minus 311,400 joules minus 298 Kelvin times the minus 232.5 joules per Kelvin. We find the delta G0 for this reaction minus 242.1 kilojoules. The log of K is delta G divided by RT. So the minus 242,100 joules divided by 8.314 divided by 298 minus 97.72. So K is e to the minus 97.72. That's 3.6 times 10 to the minus 43rd. And finally, at what temperature or approximately would this reaction stop being spontaneous? So T would be approximately delta H divided by delta S. So minus 311,400 joules divided by minus 232.5 joules per Kelvin, 1339.354, etc. So at approximately 1340 Kelvin, this reaction would stop being spontaneous. Multiple choice. Everybody loves multiple choice. Circle the best answer to complete the following statements. Reactions with these parameters are never spontaneous. That is, endothermic reactions that result in a loss in entropy. In the Fallon galvanic cell, what is happening? Protons are being reduced at the cathode. Nope. Carbon's the cathode. There isn't any hydrogen ions over there. Hydrogen is being oxidized at the anode. Yep, that's what's going on. Copper is being reduced at the cathode. No, copper ions are being reduced at the cathode. There's nothing happening to the copper at the cathode. And finally, carbon is being oxidized at the anode. Well, it's at the anode, but nothing's happening to the copper, or to the carbon rather, because it's an inert electrode. Which of these is the best reducing agent? We simply have to go through and look at the potentials on the table. Obviously, the bromine and the nickel plus 2 aren't capable of reducing anything since they don't have electrons to give away. That simply makes it between the nickel and the bromine, and the nickel has the better potential as a reducing agent. Which of the following materials has the largest absolute entropy? Well, copper is going to be a solid, room temperature. Nitrogen is going to be in the gas phase. Water is a liquid. And sodium fluoride is going to be a crystalline solid. And so by far the one with the greatest options about what it is doing is going to be the nitrogen. It's going to have the largest absolute entropy. Gold, 199, has a half-life of 3.5 days. How long will it take a 2.4 gram sample to decay to 0.22 grams? Well, we have to go through our equation, take the ratio, the log, multiply by the half-life, divide by 0.693, and we're going to find out that it's going to take between 8 and 12 days for that reaction to take place. Which of these could act as a buffer? A buffer requires a weak acid in its salt or a weak base in its salt, one or the other. First one, sodium hydroxide and sodium chloride, is a strong base in a salt. That won't go anywhere. HCl is a strong acid in a salt. That won't do any good. HF and KF is a weak acid and its counterion, so that should be a buffer. And finally, nitrous acid is a weak acid. HBr is a strong acid. That won't buffer either. Which brings us last but not least, which of these particles has the highest average velocity in room temperature? And that's simply a question of who's the lightest, and that, of course, is the ethane. Define the following chemical terms. Standard state. Standard state is the lowest energy form at 1 atmosphere and 25 degrees Celsius. Triple point. Triple point is the temperature and pressure, where a substance can be in any one of the three phases, solid, liquid, or gas. A Lewis base donates a lone pair of electrons to form a coordinate covalent bond. The cathode. The cathode is the place in an electric cell where reduction takes place. It attracts cations, and the electrons are coming out of the wire at it. Third law of thermodynamics sets the entropy scale. The total entropy of a perfect crystal at 0 degrees Kelvin is 0. And finally, problem 7. The E0 for the following galvanic cell is plus 0.48 volts. Answer these questions. What is the E0 for the vanadium reduction potential? Well, the total potential of the cell is 0.48 volts. That's the oxidation and redox part and the reduction part of the potential. We don't know what the reduction potential is, but the reduction potential for the chromium is minus 0.74 volts, but it's running backwards. So plus 74 volts. And so the E0 for the vanadium must be minus 0.26 volts. What's the delta G for this reaction at 25 degrees? Well, delta G is NF epsilon minus NF epsilon. It's a 3 electron transfer, 96,485 coulombs. The charge is 0.48 volts. And so the delta G0 would be minus 139 kilojoules. And finally, what's the EMF for this cell? With the following concentrations, we have to use the Nernst equation. The E0, 0.48 volts, minus 0.059 divided by 3, because we said it's a 3 electron transfer. Log of vanadium plus 2 concentration cubed times chromium plus 3 to the first divided by chromium plus 3 cubed times chromium 1 gets us the value, the log 7.40, and so the total potential 0.33 volts. And so that concludes our final lecture for AP Chemistry 3 of 3 in the spring 2020 with Dr. Petty. Now you can go on and have a great time the rest of the summer.